first of all, think about this. If I look from here, you've got to tell me if my eye is here, is this turning from my view clockwise or anti-clockwise? Go like this, right? So counterclockwise, like that. Or you can look at the green arrow here, right? And it's not more than a common sense that a motor must be able to turn smoothly, right? It won't turn like this and then go backward, right? This is not a motor. Motor must go in one direction. This is common sense, okay? So in that case, if this part always go in, this part must always go out, and this direction of force cannot be changed. It must be the same every second when this motor is working, right? Okay, so now what we want to do is we want to figure out how come this will work. So first part is we want to look at the B field maybe. This is north, this is south, so the B field is pointing down. You can see from the red arrow here, pointing down for the whole part. So how come this wire will go in? Can you tell me how come? The upper part. How come the force will push it in? If you have a force, that means there must be, and also you have B field, that means you must have current as well. Very good. And now is the problem that whether current go to the left or to the right. If you check that with your hand, if force is going in and B is going down, then current must be to your right side. Is it? The green arrow is the force going in. Yeah? So B is going down. Current must be going to this direction. So current. Yeah, the white arrow basically. Yeah. And which one come out first actually? Do you have force first or do you have current first? Force. Let's make a vote. Of course, B field is always there. B field must always there. Permanent magnet. The problem is, do we have current first or do we have force first? Who think force? We have force first. Who think we have current first? Very good. Common sense again. If you have a motor, if you go and buy a motor, how can you make it move? You need to plug in the wire, plug in the battery. With the current, it will move, right? What is the thing you call? Just simple English. What is the thing you call when you give them movement or a force they give you current? How do you call that? Not exactly battery.
Motor. Supply.
This is motor. This is definition of motor. That you give them electricity, they give you movement. They give you the force. What's the opposite one? You give them movement or a force, they give you electricity.
Convert.
What do you think? A word start with G.
Generator.
Generator, very good. Yeah, so this is something that you will learn in the, not today lesson, but I think this is something that you can bear in mind first. You can bear in mind first. What we are learning is motor. In terms of energy, what is changed to what energy? What energy to what energy? Electrical, can you write this down? Electrical energy to kinetic energy, KE, right? That's for a motor. You may not need to care about DC or AC first, just motor in general. You give them electricity, they give you movement. Electrical energy to KE. And for a generator, how is the energy conversion? Opposite. So you give them KE, you need to crank, right? If you have been to the science museum, you have to crank. Or you move something. Like, you think about what you learned in year 9 as well. The hydroelectric. Remember?
Yes.
Hydroelectric, wind power, fossil fuel, nuclear power plant. Those are the steam giving out the KE, and you can have electrical energy. So we are actually going to look into how we can make a generator later on as well, but not today, but later on. And that's coherent with what you learned in year 9. Back to here. So as you said, currents come out first, then we can have force, right? What defines the direction of current in this diagram, in this setup? It depends on what? Well, this is annotation only, but physically, what determines the the positive or negative pole of the battery, right? So just look at the battery. This is positive, so current come out here. I just try to trace it, and then what happened to this?
It pushes the wall.
What is this thing? You can help me to find out the name of this later on, but you can see this is rotating. And can you guess why there is a different color here? This is red color in the middle. These are yellow color. Why do we need to have something like? Why not the whole thing yellow? It's something to do with conductivity. Which part are conductive? Of course, the yellow part, right? The red part are insulation. What if this is conductive as well?
It will just pass through the wall.
And yes, if the red part is conductive, this is a useless device. The current will just go straight without passing through this.
Provide heat.
Yeah, provide heat, yes. Still useful, yeah. But this is not a motor anymore in this case. So that's why this part has to be an insulation. That means you cannot go jump directly from here. It has to pass through the whole coil. You can imagine these are the big coil here. So if I try to trace this, again, from positive to this, does it match with our conclusion previously, yeah? And now, when you go to the bottom, how is the current compared to this? Is opposite, very good. Just now, in the previous page of the note, I asked you, if the B field is the same, but now you reverse the current direction, what will happen to force? Very good, the force will reverse as well. Yeah? If you don't trust me, you can still use your hand rule to find out. But I think you should be good enough, intelligent enough to know it has to be out now. If you don't trust me, you can try. It should be out. Okay? So what's your mission? Your mission, if you want this motor to keep rotating, that means the current must be kept like this. Always go to this side. This side, always go to the left. Does it make sense to you?
Yes.
Yeah? Let me try to play the video, animation, try to get some feeling. Keep can be have a new part of video. Okay, start right away.